Thanks, Michael. Good morning, everyone. My name is Morteza. I'm a water resources engineer at the California Department of Water Resources Sustainable Groundwater Management Office. And today, I'm going to talk about modeling after in-situ soil moisture and satellite soil moisture. This is kind of different perspective of soil moisture variation in space and time. So the main motivation for me to start this work was the Vadose part of our groundwater model in Department of Water Resources, DWR. And when I started this job and looked at the Vadose part of the model, I found this is way too simple for me as a soil physicist, because we always deal with a lot more complications in the unsaturated part of the system. And basically, in our model and many other models at large scales, I'm talking about groundwater models, you see Vadose is forced to have a downward gravitational flow. So basically, you see Vadose is treated as a pathway to deliver surface water to groundwater. And this is basically ignoring soil physics aspects of the unsaturated zone. And I will show you today that this gravitational flux assumption can lead to significant errors at large scale groundwater models. And this is something many groundwater models may not believe and say, okay, unsaturated zone, so this forced downward gravitational flow is just fine. But I had the arguments with many people in this domain of modeling that this is not fine, and it can lead to significant errors. So mathematically speaking, if we look into the Darcy and flux relationship, we have flux composed of two terms. The first term is gravitational flux, which is the unsaturated hydraulic conductivity function. Second term is the diffusive flux, so diffusivity times gradient of soil moisture. And at larger scales, if we want to calculate this diffusive flux term, it will need sophisticated numerical schemes and iterations. So that's why most groundwater models, they assume this is negligible, and we have basically a uniform soil moisture profile, basically zero diffusive flux. So that's why, so computational demand is the main reason for ignoring this term in Vadose. So we have two types of conventional Vadose models at larger scales. The first one is kind of bucket model, or tipping bucket model, or whatever you call it. For example, in our model based on the IWFM engine, so we have, for example, divide the unsaturated zone into 3 layers, and then we have surface flux coming to first layers. This is our known boundary condition. And then they want to solve soil moisture in layer 1 and outflux in layer 1 F1. And because they assume outflux F1 is a function of soil moisture because of the gravitational flux assumption, so we just have one unknown and can solve this without any iteration, go to the next layer and go to the next layer until we reach the groundwater table. So this way, we can have a very fast algorithm for Vadose part of the model, and this is what they need, because at large scales they cannot really solve full Richards equation. It's going to need a lot of computational demand. Second common approach is the kinematic wave assumption, kinematic wave model, or kinematic wave approximation of Richards equation. For example, we see this in a ModFlow UZF package. So this is basically Richards equation, but again, dropping the diffusive flow term. So again, this is forcing downward flow in the Vadose. So our model is called C2 within fine grid, and it's based on IWFM engine. in Central Valley, California, and is simulating surface water and groundwater for the whole domain. So as I mentioned, our current Vadose part is a bucket model. And as I will show you, this is what I don't like. And then the alternative would be full Richards equation. This is what the DWR doesn't like because it's computationally demanding. So that's why I worked over several years to come up with something that is close to full Richards equation because it's accounting for the diffusive flux, but as fast as bucket model. So we do not need sophisticated numerical schemes. So this is the Darcian flux. And my key idea was that for calculating the gradient of soil moisture in space, we can use the diffusion type of equation. And then from that, we showed that the gradient of soil moisture can be estimated from the temporal change of soil moisture. So this box is supposed to be equal sign. So with this, we propose this flux model. So we have gravitational term, and then we have the diffusive term. But the trick is that for the diffusive term, we do not need gradient of soil moisture. We can just have soil moisture variations in single layer in time, and from that, we can calculate the gradient of soil moisture. And in this equation, we have half-order derivative term that can be simply calculated from its mathematical definition from time series of soil moisture. And this C is an empirical correction factor, and we set it to universal constants of 0.5 when we have a downward flux and 2 when we have a upward flux. So this is coming to modify some of our simplifying assumptions. So now we want to route soil moisture and flux in the unsaturated zone with this flux model. But the challenge is that when we have a gravitational flux model, as I said, it's always downward. So it's very straightforward to have a layer by layer sequential calculation. But now we have a two-way flux. So the flux can be downward or upward. And so it was initially challenging for me to come up with an algorithm that can accept this model. At the same time, we do not have iteration. So we just want to solve layer 1, go to layer 2, go to layer 3, and go to the next step. So then after a while, I came up with this strategy. So let's focus on layer 1 for now. So we have F0 is boundary flux coming. It can be precipitation minus runoff minus ET. And for layer 1, we can write this mass balance equation, A. And then we have this proposed flux function in equation B. And if we combine these two equations, we get equation C. And in equation C, we have only one unknown, which is soil moisture in layer 1. So we have one equation, one unknown. So we can simply solve this equation. So it gives us soil moisture in layer 1. And once we calculate soil moisture in layer 1, we go back to equation A. F0 is known, theta 1 is known, and we can calculate F1. So once we calculate F1, we have the influx for second layer. We can write the same or similar set of equations. Equation A, mass balance for layer 2. Proposed flux equation for layer 2. And then in combination, we get equation C. And in this equation, we just have one unknown, which is soil moisture in layer 2, theta 2. Again, we can, with this one equation, one unknown determinant system, we can solve theta 2 and then go back equation A, solve F2. And this way, if we have any number of layers, we can go just layer by layer. So we do not need iterations. And we keep doing this calculation until we reach the groundwater table. And the flux hitting the groundwater table will be our groundwater recharge. So based on the upcoming recharge, we update the groundwater table for this time step, and then go to the next time step and do the similar calculations. So I call this model Vadose analytical algorithm, or VISA. Now I'm going to show some numerical test of the VISA, and my reference is Hydras 1D because it's solving full recharge equation, and we want to be as close as possible to the full recharge equation. So I got a 15-meter soil profile for this example. I assume 100 nodes, computational nodes for Hydras, and then initial groundwater table at the middle of the column, and then I assume an initial soil moisture profile in equilibrium with the groundwater table. So for boundary conditions, I assume 10 years of sinusoidal soil moisture variations is a theoretical input. And top boundary, bottom boundary, I assume 0 flux. And I assumed the same boundary conditions for the VISA and IWFM, the same set of soil hydraulic properties, everything the same. But for computational layers, I just assume we have 3 computational layers: layer 1, layer 2, layer 3, from 0 to 50, 50 to 500, and 500 to 1500 centimeter. Okay. Yeah. So before jumping into the VISA results, I'm going to show you a few slides showing the IWFM calculations of the groundwater table variations. So the black line is the true solution coming from Hydras, and the green line is the IWFM simulations based on the gravitational flux assumption. And for this, we have a specific yield parameter that we assume for now it can be a fitting parameter to fit Hydras results, and we get the green line. And as you see, we have some deviations, and also we have smaller seasonal variations coming out of IWFM. And this is mainly because the fitting parameter SY is way too large, so it's larger than porosity, which is not physically possible. But here is fitting parameter. And this inconsistency is because of the gravitational flux assumption in the Vadose part of the model. So in another scenario, I try to capture the same temporal dynamics by reducing the specific yield parameter to half, 0.3. And after doing this, you see, after the initial condition, you see this big jump. It's like, how much? It's 8 meter. 8 meter jump. This is because we have an initially wet profile, and when we start, we have a gravitational flux for the Vadose zone, and it's going to dump all the water to the groundwater. So that's why we get this big jump. So here we have a smaller jump because we fitted the SY parameter. And for this scenario, we see everything is very similar. So the temporal dynamics of IWFM is very similar to Hydras, except this very big jump at the initial times. Then I tried, okay, this big jump is because of the initial soil moisture. What if I remove the initial soil moisture and assume in IWFM we have a dry soil profile above the groundwater? And this is what I got, the pink line. And as you see, it's getting closer to Hydras, but we have some deviations here. And basically, we have a phase lag. And this is because this makes sense physically because we have 7.5 meter of the profile, which is fully dry, and precipitation is going to fill this up. And then it goes to a closer solution. And so this doesn't work. I can say it's getting closer. And another scenario, I said, what if I do a warm-up? This is a common practice in groundwater modeling. They said let's do it. Let's run the model for 10 years, 20 years. And I did that, and it didn't work. And you see the blue line, the groundwater is going above the ground surface. So I'm showing all this because it's hard to convince groundwater modeling community that Vadose is important. It should be treated way better. So let's see what my proposed algorithm Visa is doing. So I'm showing here the groundwater recharge, temporal dynamics, and the groundwater table variations. As you see, after accounting for the diffusive flux, it's getting much closer to hydrous. So my point is, the main reason for the errors that we get in IWFM is mainly because of ignoring the diffusive flow in the unsaturated zone. And here I'm showing the soil moisture simulations out of the three models. So hydrous 1D, the red line is our reference. And then we have IWFM, and then we have Visa. As you see, Visa soil moisture is much better than IWFM because of all the errors I discussed. And as you see, there is a tendency in IWFM to underestimate soil moisture. This is because if it wants to have the true solution for soil moisture, the flux will be too large, because it's say, okay, so flux is unsaturated hydraulic conductivity as a function of soil moisture. So if you have a high soil moisture, okay, 16 minutes, I have my time. So yeah, improving soil moisture, and also discuss the layering effects here. Yeah, because of time, I'm gonna skip this. So I just wanted to say I showed that this strategy, so initially derived for uniform soil profile, but now I showed that it can also, with accepting some levels of errors, it can work for a distinct distinct layer soil profile. So it changed different Van Genuchten parameters, and Visa could still follow the hydrous 1D solution. So we have advantages and limitations for this proposed Visa algorithm. Advantages is much faster than numerical solvers of Richards equation, and it's much more stable because with only 3 layers, I can get the solution. This is impossible in full Richards equation, hydrous or similar models. And then the limitations. So because of all this property of the model, I'm proposing this for large scale applications, because it's just as fast as the gravitational flux model or bucket model. And then limitations is less accurate than numerical solvers of Richards equation, of course, because we have simplifying assumptions, and less accurate when we have a distinct layering. Yeah, that's all I have for today. I will be happy to take any questions or comments. Question from Morteza? You go first.
Okay. Yeah, just curious if you consider about horizontal direction. You just show the vertical propagations. So how about the horizontal direction? Yeah, 2D. And now, go ahead.
1D, because our original model is 1D. I haven't worked on the 2D version of it, but it's a research for later. But in most of the groundwater models, they assume 1D flow in the unsaturated zone and then 3D flow for the saturated zone. So this is the common practice, and I followed their strategy.
The R term warm up actually means spin up, right? The model spin up. Yeah. You said warm up. Yeah.
100 years is enough? I'm not sure if I understand your question, but this is common practice. They start with any initial condition, and then they warm up the model for 10 years, 20 years or so to get the actual or the better representative initial condition. So this is what they are doing. But this doesn't work because we still miss the physics of flow in unsaturated zone. Even with spin up, with tuning, with everything, we can get it closer to the reality, but we are actually, we are just fitting the model to the actual reality.